Maximization. First, just two quick announcements. One announcement is we are a little bit behind schedule. We're going to try to make up for this by possibly shortening the breaks in the afternoon just a little bit. So we'll do our best to keep everything on track during the technical sessions. There will be 15 minutes roughly for the presentations, 5 minutes for questions. And the other announcement is that for dinner tonight, there's a bus. The bus is going to leave from right outside of the building at 7. It'll take us all to the restaurant. And the bus will come back eventually, but if you want to, we can also stick around afterwards on our own. Some of the students who are local or when you want can help write down the name of your hotel on the card. If you want to take a taxi back later on, take a little bit of time to explore around the Westlake. The restaurant is right around there. All right, so without further ado, we'll get started with the technical program for this morning. The first paper is going to be presented by Peter Terlicki. He's going to talk about the paper, Should I Stay or Should I Go? Maximizing Lifetime with Relays.
Okay, thank you. So if you're contemplating the question, should I stay or should I go, I hope you choose staying. So let me introduce the problem setting. So a transmitter would like to transmit information to a receiver. So what we do is we place in mobile relays along the line of communication between the transmitter and receiver. So those are B1 through Bn, and then you have the receiver there at B0, and then you have the receiver. The transmitter at B0, and then the receiver. So the initial battery power of node I is Bi, these are battery power nodes, and mobile. And then you also have initial transmission range for node I, which is Di. So that's given there. Now, communication drains battery. So standard assumption is that the power spent is d to some alpha energy per time unit, where alpha is some constant greater than or equal to 1. And then mobility also drains battery, and it drains battery in proportion to the distance traveled. So the farther you travel, the more battery you spend. And then we also, so these relays move, and we restrict them from kind of switching order. And the reason for that is they're kind of physical systems where relays kind of move along a track where they can't switch order, they can't swap. But they can theoretically occupy the same location. And in that case, one of them is shut off and the other one transmits. So it's a way of kind of powering down one of the relays. And so we introduced the maximum lifetime of first step problem, MaxFD. And so in this problem, relays are to be deployed at time 0. So we only allow movement initially at time 0. Afterwards, they can't move. Once they arrive at their destination, they can begin transmitting, and they transmit until one of the relays dies, at which point the network is considered dead. Relays can't readjust their transmission ranges in this problem. We'll see later on in the next problem, we allow transmission ranges to change. And the goal is to maximize the lifetime of first step. So again, relays can only move once at time 0. Once one of the relays dies, all the battery is drained, that the network's dead, and we want to maximize the lifetime of this network. We call it the lifetime of first step. So we can represent it by the following nonlinear and non-convex program. We want to find the location maximizing lifetime positions, y1 through yn, which maximize the minimum lifetime. And so maximize the min of B0 divided by y1 to the alpha is the lifetime of the transmitter if the first relay is located at y1, because the transmitter must transmit to the first relay. So that's the first expression. And then B1 minus A, X1 minus Y1, absolute value, is, that's the amount of battery drained, that's the amount of battery left over after movement to Y1 from X1. Again, the initial position is X1. So the next problem is the maximum transmission lifetime problem, MaxTL. And what we can show is that we don't need to move between deaths. So we don't need to move unless someone dies. So potentially, what we want to do is we're really interested in trying to maximize the lifetime of the transmitter. How long can the transmitter communicate to the receiver? So in this case, we allow transmission ranges to close gaps in communication. So in other words, transmission ranges can readjust to cover that gap that was caused by the dead. And the question is, what set of positions or ranges maximizes the length of time the transmitter can communicate to the receiver? So, and this is the transmission lifetime. So now we'll analyze the no friction case, and by no friction I mean there's no cost of movement. So in other words, if I were to drop these relays from a plane or position them somewhere, where should I position them to maximize lifetime? Either transmitter lifetime or lifetime of first death. It turns out that if Li is the lifetime of the first node, you should position them so that all nodes die at exactly the same time. So everyone should die at the same time if you were to position them and movement didn't cost anything. And just kind of the overview of the proof. We can show that any optimal solution has fixed transmission ranges for the duration of lifetime. What does that mean? Well, fixed transmission ranges means they don't have to vary their transmission ranges as they move, so they remain fixed for the lifetime of the network. And then we show that of all solutions with fixed transmission ranges, the solution in which all nodes die at the same time is optimal. Because if they did die at the same time, the transmitter must die before some other node, because we're assuming fixed transmission ranges. So a node can't die before the transmitter, because otherwise another node would have to extend and the transmission ranges wouldn't be fixed. So and then we have a theorem if, in the case of no friction, an optimal solution is obtained by placing relay I at, is by having relay I have transmission range D times the alpha through VI with the sum of the alpha roots. And then we give the corresponding lifetime. But the important point is that all relays die at the same time, and then this is just an algebraic expression expressing that. So if A equals 0, there exists a single deployment and a no swapping optimal solution for max TL. In other words, when there's no friction, relays don't have to move. All they have to do is move once, and they can stay at their positions for the duration of the network lifetime. Okay, so now we're going to move on to the case where there is friction, to the discrete max FD problem. So this max FD problem, just to recall, is the problem of maximizing the lifetime of first death. Once a relay dies, the network is considered dead. In discrete max FD, we discretize the interval from 0 to D into m subintervals of the same size. And we assume relays can only be located on one of the grid points. So we discretize the line, and the relays can only move to one of the grid points. They can start anywhere, but they can only move to one of the grid points. And we can show there exists an optimal dynamic programming algorithm for max FD on grid points. So we can give an optimal dynamic programming solution. And the idea is the following. We try to solve all possible instances for covering the prefix segment 0 to the jth. To the jth position for all j between 0 and m, using the I closest relays to the transmitter. So, in other words, let Fij be the lifetime of first death of the solution of the first I relays transmitting to j, to partition j. And then we solve this instance, and then the desired final output is FNM. So here's the recursion. Let me just kind of express the idea. So again, we look for the lifetime maximizing position of the ith relay among the j+1 first possible positions. When a position is examined for the ith relay, we use the optimal locations for the first I-1. So what we do is we think about putting the ith relay on any of the first J partitions. And when we do that, we consider the optimal of the previous I-1 transmitting to that point where that ith relay is. And this is Fij. The running time of this algorithm is O of nm squared. We also devised another algorithm which is not dependent on m. We call it lifetime binary search, and this is a parametric search algorithm. So what we do, it turns out to be an FPTOS for max FPM grid point, but let me explain the idea behind the algorithm. So it's a search on potential lifetimes. So given a lifetime t, I can tell you whether the system can reach a lifetime t or not. And then I do binary search on the possible values of t. So what I do to determine whether t is feasible or not is I start with the rightmost relay. So I have a line 0 to d. I start with the rightmost relay and move it back as far as I can until that has lifetime exactly t. And then I do this for all relays previous to that. Now there's some problems. The last relay can potentially bump into one of the previous ones. In that case, you have to kind of move all of them, so it's expressed. You have to kind of move all of them back until either one dies or this last one is lifetime exactly t. So this is the idea though. And then we can show that dynamic programming algorithm and lifetime binary search, or FPTOS, for max FP if initial battery sizes are not so small. So an FPTOS is, in other words, this solution can be within 1 plus epsilon of the optimal, with running time a function of 1 over epsilon if initial battery sizes are not too small. If battery sizes are small, we can show an example where this lifetime, the difference between the lifetimes is large. So this is the lemma expressing the FPTOS. For any epsilon in 0 to 1, if bi is large enough, and m is some function of epsilon and n, then the optimal solution is within 1 plus epsilon, it's the alpha plus 1 of the solution on grid points. So it's a little bit stronger because you have the alpha plus 1 power there. So we're going to move on to considering the maximizing transmission lifetime problem. And this is going to be under the move once model. So in this model, again, relays can move more than once. Once a relay dies, relays can move or to kind of adjust their transmission ranges. The question is there an algorithm to maximize this transmission lifetime? We don't have a solution for that, but we did perform some heuristics. One of the heuristics we performed was, well, we know the optimal solution when there's no friction. So let's consider moving all relays towards the optimal solution, and let's find the lifetime maximizing positions from that standpoint. And again, here we just restrict relays to moving once. So let me kind of explain the graph a little bit. So these are a bunch of different algorithms. When there's no friction, the x-axis is friction, so friction increases from 0 to 10 in this case. The interval is 1 unit of length wide. All the relays, there are 4 of them, have 1 unit of battery power. And at 0 friction, they're all optimal. All these algorithms are optimal. And as we increase friction, they fall off a little bit with the NLP algorithm and the exponential algorithm. So what we did is we break the interval up into m subintervals, and then we brute force test every possible combination of n relays on those grid points. That one performs best, and the dynamic programming doesn't perform as well. But again, this problem is a transmission lifetime problem. We have no theoretical results for this problem in dynamic programming. We know that dynamic programming is optimal on a max FD problem, but we don't know about this problem. And then open problems in future work. We have a couple of conjectures which we want to prove. The last one was actually proved recently. And we can show that if relays are initially positioned at 0, it's optimal for them to be ordered in increasing order of initial battery power. And what happens in a model where we can swap or deactivate and activate the relays. And then consider the model where relays can be located anywhere in the plane. So thank you.
Time for a question or two?
First, you just consider one, the relay load and the destination is, single line.
Yeah.
The real network is random deployed, either, in the rectangular area or the circle area.
Yeah, we left that to future work because, again, we considered this problem, solving this problem before moving on to something more.
So, in terms of from an application background, from my mind, maybe just narrow road useful. Otherwise, it's function single line. That's not realistic in most cases.
Right. Again, this is more of a theoretical paper, and also, again, there's some uses in that. If you deploy them on the line, you want to maximize the time the transmitter can communicate, so they're passing along the information. And so in that regard, it's...
If I can make a comment on
Yeah.
that, actually just saying that this can actually be practical, because there are, for example, situations in a mining, for example, where you want to deploy some relays to reach the top destination, and so you actually have a topology that is aligned to both. So in some cases, you might actually have some
You see, under was the mining, right?
yes,
Mining, I think that
but it's still a narrow
Yeah, really
Canada
standard
is not
some sort of
reliable.
Yeah. Because initially, if you were to start all relays at 0, where would you send them? You send them along the line, of direct line communication. So, in that regard.
I guess another sort of generalization would be to go from single transmitter to single receiver, now to have multiple transmitters to
Exactly.
one receiver, but with relays helping multiple transmitters.
Yeah, right.
Any other questions? Okay, if there's no other questions, then let's thank the speaker one more time. And as the next speaker is coming up, I'll just make a quick announcement, which is that please make sure that you contact your session chair before the session so that they can give you any instructions if necessary. We'll also we'll all be trying to present from the same laptop, just to make the transitions between presentations a little bit smoother. All right. So the second presentation in the session is for the paper Network Lifetime Maximization in Delay-Tolerant Sensor Networks with the Mobile Sync, and it will be presented by Rick Valier.
This actually is John work with my student shoes and Professor Yun Xu from the University of Science and China. So I think here are just the sketch of the time. So basically, traditional sensor network, you have a fixed sync. There have several hundreds to thousands of sensors. You got a tree or a flow go through that. But the sensor they are to the sync has to relay data for others, not just themselves. Usually they deplete their energy much faster than the other sensors. So in the end, because of uneven energy consumption among sensors, some will die early, some become despite you have plenty of energy, but become useless because your data cannot transfer to the base station. So instead, mobile sync, this concept is explored by people, because mobile sync can improve network performance in many aspects, including like network uptime, connectivity, data delivery, reliability, and throughput significantly. So in this paper, basically, we try to explore the mobile sync and mobile ability. Okay, so. There have extensive study about the mobile sync in the past 5 years. Most of the study, for example, you assume the mobile sync can move around in the monitoring area, anywhere, any point. In fact, if this is monitoring area, they have a pond, maybe it's a big rock, a big building, you couldn't move to that particular location. Actually, the moving location is bounded, restricted. The other issue is most, consider network lifetime, do not consider data delay, because you move around for particular sensor data may not send it to the base station. You move, you couldn't reach it. Maybe your data stored in the sensor for a moment, then later the mobile sync collect the data. So this means the data, not real-time collected. They have some kind of delay. Which kind of delay you tolerate? Because you deploy such a network, you want to get the data as soon as possible. The third one, mostly the current study, usually form this problem as an integer programming, then developing, solid mixture or integer program. Most cases is, computationally very expensive, just for small or medium size, but poor scalability. So what we do, we assume in this paper, we aim to find, the particular mobile sync initial deployed in somewhere, then travel the region, come back, find a close trajectory, maximize network lifetime. But we have some constraints in the mobile sync. For example, the space, in this region, only some strategically point location you can move around. The second one, I cannot, give the tolerant delay bound. You just in this amount of time, you must be come back. Also, each sensor, because the mobile sync is a different position. Some sensor may be reached, maybe not. Because we bound the sensor reach the sensor to the particular mobile sync with H hops. You must, if longer hops, there is data maybe, because of poor link reliability, then the data later collected by mobile sync. So, for this, basically we can say the network is considered a stationary sensor. Air is the space, all the locations the mobile sync can move around. Usually this potential location is much less than n. Okay. The mobile sync initial is located in default side. Maybe it's outside your monitoring region. For example, you use a car, maybe use in the overnight, put in the garage. It travel and secure only at a location in air, okay? For data collection, will return to S0 in the end. This may be recharge battery, maybe refuel petrol, because mobile sync is mechanical moving, okay? All sensors have identical data generation rates. So before we give exact definition, we define H-hop labels. Suppose mobile sync in our potential location S, we use a capital H, NHS means all sensor, can reach this location within H hops. That means H or less than H hops. Okay, so this is, for this we can use breadth search to get every location like NHS. So specifically we define a problem like this called hop constraint mobile sync problem. So in this one, we aim to find an optimal trajectory for mobile sync consign sync locations in here, make the network life maximize, but we have these two constraints. The first one, each sensor must send its data to one of these locations with no more than H hops. This is so-called hop constraint. The second one, the maximum tolerant delay or data delivery is bounded by this. That means, in other words, if we are let this trajectory length is L, the mobile sync will assume travel in the constant speed v, so the Dmax should be is L divided by v. Satisfy these two conditions, subject these constraints, then you try to maximize network lifetime. So this problem is empty hard because we can easily reduce so-called travel salesman with neighborhood problem to this problem in polynomial time. So because time limit, I wouldn't to talk about that. So basically, because this problem is a hard problem, we couldn't find an approximation algorithm for that. Instead, we try to find, heuristics algorithm. This algorithm we decompose this joint optimization problem into two sub-problems. The first one is to find, optimal hop constraint treasury, meet the given data delivery constraints. Then the second step, because our aim is maximum network lifetime, then once this location we already found, how to arrange the sensor to this location, we try to find the load balance routing tree to balance each node the energy consumption. So this is basic idea. So what we do, the basic idea is, we construct the treasury is, each time this is supposed to currently of the location set in this treasury S prime. Each time a new location is not here, we add to here. So this addition should meet the delay constraints, the first thing. If they have multiple such candidates, we try to choose one of these locations with the maximum benefit. The benefit I will define in next slides. If, in the end, we already found this one. If the founded treasury with the deadline, delay deadline cannot cover all sensors, because we require each sensor to one of the location no more than H hops, then currently this H is not enough. You need to increase by 1. So the benefit of the function is like this. Suppose we choose S double prime joined in. That means within the H hops, in this location, how many sensor can cover, and minus, all of this sensor has been covered by previous locations. Then divide by, from previous, the last one is S prime, any of the location. This is the distance. Basically, per unit length, how many new sensor be covered in this case. We try to find one of this location with maximize this one function we call maximum benefit. This is our heuristic. So the algorithm is quite simple. Initially, each time you add the node to here, basically you construct a tree structure. Like once you get this set, it's because we talk about geometry space. So we can, this is complete graph. Then we try to find a minimal spanning tree T1. Then from this minimal spanning tree, for all old nodes, we put 2 copies. One is X, one is Y. From X to Y, if X not equal Y, their distance is supposed is weight. Then we try to find minimum weighted perfect matching in this bipartite graph. Then the T1, plus M, the union form a Una graph. From here, we can try to find a treasury, through the triangle, inequality. Then we get an A prime. We check the A prime whether larger we given the bound. If not, that's one feasible solution. Otherwise, this is not. So once we got this one, if we can further add, new location here, that's, the delay constraints not violated, we continue doing so. Because you get more sync locations, the workload shared by these guys. So the longer network lifetime will be. So that's the first step. We already find a feasible, treasury, include all sensor, load more than H hops. Now, for some, locations maybe more sensor, some is less. How to evenly distribute the sensor to these locations? So we equivalent to find a load balance routing tree. We virtually look at, each this kind of sync location is like a road. All of the children, the maximum energy consumption should be minimized, because every distance should send the data through this node, they maximum consumption energy. So we try to minimize the maximum one. So doing this, basically we created a virtual node, this is a virtual one, and put all of the K, choosing the location to compress to this node. That means all of the sync location, the children actually is a sensor. You become the children of this one. Then you build a balance tree. So then you try to, this case we actually solved a load balance semi-matching. This algorithm due to load is 2005. So it's basically an algorithm like this. First you construct a virtual node, collect all of the sync nodes together, then find approximate load balance tree. This is problem also we proved is NP completed in the IEEE last year. Then we construct, this step of constructing this. In the end, we can implement, regular tree is balance. That means the maximum energy consumption, particular sensor should be minimized. So we conduct some experiment, this is 100 to times 100 meters, sensor node from 100 to 600. So we also use another heuristic comparison. Once delayed sync, initially include all of the possible locations. Then the delay valid. Each time you remove one of them, in the end, make the delay satisfied. The other one is initially you try to, from these locations, you try to find a set, with a cover all the sensor in each host. Then you try to, build this kind of, basically all the difference in the first step, the trajectory finding. So in the end, what we achieve, this is three different ones. This is our heuristics. This deleted sync, this set cover. Certainly this algorithm much better. Longer delay means longer lifetime, right? Because you have tolerance. But from the scale, this one much better than the rest two. So we can look at here. This is the red one is our heuristic. This is another two, pink and blue is another type of the algorithm. We also investigate the H and A relations. H, remember each sensor to one of the sync location, the maximum hops bounded by this. From here, you can see in the very beginning, there's a big difference in lifetime under 200 nodes. With the increase in the node density, all of these algorithms, converge in the same point. The reason is, once you're doing this, they think is high collectivity. All of the sensors can be in the edge hops reached. So that can explain this point in here. So we have doing this one, that this we just look at different H, okay? So from here you can say H equals 2, you get a much longer lifetime. H equals 5, you get a lower lifetime. That you can reasonably think about. Because if H is large, the number of distance become larger. So each road children become very heavier load. In small H, lighter load, then you have a longer lifetime. So that's about this. So here we also compare the three algorithms. So I think my time is running out. So basically we have showed, formalized this joint optimization problem. We show the problem is NP hard. We deliver our heuristics, okay? We conduct extensive experiments. We also, the proposed algorithm outperforms another heuristic significantly. So this is our work. Well, our next step is try to, from this just talk about the single mobile sync. What about the multiple mobile sync? How to cooperate, how to deliver key, treasuries each for one of these mobile syncs.
So are there any questions?
With imperfect link quantities, edge hop does not necessarily guarantee the delay.
Yeah, you are right. If I think one of the person asking the kid speaker about Mac layer and high level. I'm talking about this high level, because later if you deal with Mac physical layer, different kind of computation model of different. Here basically I adopt graph model. In your case maybe it's so-called physical model. The SINRS type. I did not touch the underneath, physical or Mac layer. I work in the high level, network layer or above.
Any other questions? I guess one question I had was, in the initial problem formulation, you assume you have a graph where you have the two sets of nodes, N and L. And you said that typically L is much smaller than N.
The one set is central node, that's a special node.
Yeah.
Once you put there, the other is not a node, it's a potential location of mobile system. You can move what we call the strategic location or anchor points.
Yeah.
Okay, so not at this area, you mobile system can do any around. For example, this area, particular area is a pond. You couldn't put the water, right?
So my question is, how does the complexity of the algorithms that you develop depend on the size of that set out?
Basically, it depends on I think the original paper should be is n square times the number of potential locations. Yeah.
Okay, so it's linear in the size of L.
Yeah, linear with the location, but n square of problems are the nodes. Yeah.
All right, so let's take speaker one more time. Great. So the next talk will be on the paper. Let me see it. So the next talk will be on the paper Achieving High Lifetime and Low Delay in Very Large Sensor Networks Using Mobile Syncs, and this will be presented by Michael Beck.
Hello everybody. So I will shortly motivate our paper. So there is a trend for ever larger wireless sensor networks. As an example for environmental monitoring, so we have the Screen Ops project with over 1,000 nodes, or we have the Wuxi City, the CDC project with thousands of nodes. So scalability plays a crucial role in all protocols and mechanisms by the sensor networks. Another trend is, as we have seen before, the sensitivity to delay of information transfer from sensors to things. So we want to receive our information quickly. And of course, there's the growing already of wireless sensor networks, the energy issue. So we want to extend the lifetime as far as possible. So one method, as said before, is using mobile syncs. So I will not go into the hotspot problem here because you already heard about it. But mobile syncs can only be suboptimal for information transfer delay. Why is that so? Well, if you have an optimal position for your delay, then mobile syncs means you move away from this optimal position, and then you have suboptimal position most likely. So we asked for a strategy which has mobile syncs but still achieves slow delays, and we further wanted to scale for really large sensor networks. Okay, so the outline of the talk is like the following. First, I will refine our problem statement. After this, I will give our holistic framework to you, and after that, we will go into the evaluation of this. Okay, we assume a circular area with radius r, in which we deploy our sensor nodes, order of thousands, and they are uniformly distributed over this area. The set of things has a cardinality of k, which is up to hundreds, and the thing's movement takes place on a large time scale. So for example, if it measure the temperature at night in the woods or the forest, for example, then you would place your things, take your measurements, and on the next day you would go into the forest and move your things, or let them move over the day. And so you wait for the next night and take your next measurement. So it's on a large time scale, and the movement of the thing is rather a sequence of positions instead of a continuous movement of the thing. Okay, and we say that the amount of time each thing stays in one place, we call epoch. Okay, so let's now come to our problem statement. We define the lifetime as the time until the first node dies of our network, and the delay we consider the worst case delay of the whole network. So worst case analysis of both measurements. So, and of course we want to achieve high lifetime and allow information delay simultaneously. So this is a very hard problem. Achieving only a high lifetime is already a hard problem, and we have here multi-objective, so we want two things at the same time, which are conflicting. And why this problem is so hard is we have so strong dependencies between the paths. So we have one path from the node to the sink, and you want to get the delay from the node to the sink. It's not only depending on the number of hops you take, it's also depending on how many paths interfere with your path. And the same holds also for the energy. So here's how we try to solve it. First, we reduce our problem to a geometric problem. So we have our sinks are uniformly distributed over the area. So the number of hops which we need from one sink or from one node to the sink is proportional to a Euclidean distance. It's far away, we need more hops. It's very easy. So instead of trying to reduce the number of hops, we now try to reduce the maximum Euclidean distance. Another heuristic we use is we use cells. So how do we understand this? So we have here we have one cell with one sink inside of it, and we say that one node, when it lies in this cell, it is allocated to the sink, so it means its data is sent to the sink. So by shaping these cells and trying to keep the cell's areas balanced, we can hope that there are approximately the same number of nodes allocated to one sink. Okay, and here's how our model looks like. We use an orbit model with n orbits. So this is extending, or this is building on our previous paper from last year, DCOSS, where we have used 2 orbits. So now we go for n orbits. And so this divides our network area into this polar grid you can see here. So you have circular segments in the middle, and around this you have annular segments. And if you have more orbits, you have further annular segments. So on each orbit, we place now Ki sinks. So on orbit I, we place Ki sinks. So in this example, you would have K2 equal to 7. And you see that each cell in orbit I has an inner and outer radius. So this would here be the inner radius of this cell, and this would be the outer radius of this cell. So by choosing this Ki and Ri, we can form this cell, we can make it big or thin or wide. And since all these cells look the same in one orbit, we can talk about the maximum distance in the ith orbit, which we denote by di. The movement now takes place by taking this whole thing and rotating it around the center, so the relative positions of the things keeps the same, not rotate the whole system. Okay, as said, by varying these parameters we can form our cells, so we can try to achieve different goals. First goal we try to achieve, our first strategy we try to follow is we want to minimize the overall Euclidean distance from any node to its sink. We will call this approach from now on MD, for minimizing the distance. The second strategy we follow is, again, minimizing the overall Euclidean distance while keeping the area of the cells equally sized. So we're taking our second measure into account here. So we will call this EA for equal area. Okay. So we have to do 2 things. We have think about the sync distribution Ki and the radial distribution Ri, and we have to think about how many orbits we want to use. So let's start with the first thing. So here you see the goal function of our MD strategy. So this makes of di, and you see here the di, they are quite complicated functions. And what you see also here is that we have a very large search space. So we have here all possible sync distributions you can choose from, and here are all possible radial distributions you can choose from. So we have real value parameters, and we have a combinatorial explosion of sync distributions. We tried to analyze this, and it's very hard, so we did what probably a lot of people would do. We just threw computational power on this. And this took us a really long time. It took several weeks and several computers to get these results here you see now. So these are the radial distribution for 4-orbit case. And here's the number of sinks ranging from 12 to 100. And what you see is that the optimal radius, which we get from our computations, it converges to splitting the total radius into 4 equal parts. And it does this for both strategies. Similar things happens for the sinks. So we have that, here we have that the number of sinks in the first radius, and then we have the number of sinks in the second radius, which is just a multiple of the number of sinks in the first radius. It's 2 times K1. What you also see is that in the third radius you have 3 times K1, and in the fourth radius you have 4 times K1. This is for the MD strategy. For the EA strategy we have similar stuff happening. So in the second node we now have 3 times K1, in the third we have 5 times K1, and in the fourth we have 7 times K1. So there is some pattern in here. And it also holds for more orbits or less orbits, and if we go for more things. But if we want to do that, I would not try it for more than 100 things, because it takes very long time because of this combinatorial explosion. Okay, so these are our rule of thumbs we got from our simulations. And so now we use these rules to determine how much orbits we need to minimize this Euclidean distance. So this is what we do in our second step. So again, we try out different numbers of orbits and different number for the number of sinks, and try to minimize this maximum Euclidean distance. So what we have achieved was to do this table here, where you can see how many orbits you should use for which strategy. So for example, if you have 46, and you want to follow the EA approach, you would land here, and then you would use 3 orbits to minimize the maximum Euclidean distance. If you use the MD approach, you would rather use 4 orbits. Okay, so this is our heuristic. And now let's evaluate it. So to investigate the quality of it, we had to find some competitors, but unfortunately this topic is very tapped. So there are of course works concerning lifetime, and there are works concerning large networks, but there's almost no work about concerning low delay, high lifetime, and large networks. So we have generalized ideas from earlier proposals for smaller cases or from mathematical optimization. Our first competitor is a random walk. So we just take a random step into a random direction with each sync. This is our baseline competitor. It's kind of the easiest thing you can do. The next one is auto-periphery. It is based on a paper by Lu and Hugo. This strategy we have proven is optimal for a single sync scenario for the lifetime. So in the single sync scenario, we would have one sync going around this circle, and this would be optimal for the lifetime. So we generalize this idea to our cells, and so each sync is doing its cell with auto-periphery, and the cells are formed by our MD approach. The next one is following the energy. It is very simple representative of the stated trajectories. So what these things are doing, they are just going to the nodes which this is no, which have the most energy left. The next one is the case-center heuristics. We generalize this for mathematical optimization. So there is this algorithm by Hochner and Schmois for the case-center problem, which is simply hard. And we generalize this algorithm to fit our needs. Okay, and then we have the static MD. So the last two algorithms here, they are static. The static MD just takes the best position of the dynamic MD concerning the delay and stays in it. So this will probably not be good for lifetime, but we want to see how good it can get for delay, and then also see if we move this thing, how does it worsen the delay. Okay, we analyzed 3 different scenarios with a lot of nodes, and we have the same sync ratio of 100 nodes per sync, and we repeated every experiment 10 times. So what are the results? See here for the delay and the small scenario of 1,500 nodes that our static MD is doing the best job. But we also see that our mobile approaches EA and MD, they are not that much worse. Also our case center, which we generalize for mathematical optimization, is quite good. What we see here is that the outer periphery and random walk over there, they are not so good. And now we increase the network size, so now we have to go to 5,000 nodes. And what you see is that the last 4, they did not much change, but the first 2 they do not scale, so the delay bound goes up. The same holds if we increase it furthermore, so we have 10,000 nodes here, random walk, first 2 to scale, and outer periphery is somewhere around 70 seconds, and the other 4 again has not changed much. So now let's analyze the lifetime. So here on the x-axis you can see the lifetime number of epochs. So what we want to have for a long lifetime is that these lines are going to the right side of this graph. And on the y-axis the total energy consumption of the whole network is plotted. So you see how much energy of the network was used until the first node died. Okay, what you can see here is that the MD and EA, they are doing quite good, as the others are doing not so good. What's interesting to see here is that we have 2 mobile approaches, random walk following the energy, which are doing worse than our static MD. So if you just using mobility in any fashion does not happen necessarily. So now let's see what happens if we increase the network size. So for 5,000 nodes, everything goes down, which is clear because we have this strict lifetime definition of first node dying. And we see also that EA does not scale as well as MD. The same holds if we increase it furthermore. Okay. The next graph, also you can see how these things scale. So on the y-axis you have now the lifetime, and the x-axis you have the delay bound. And these symbols are different size, which represent the size of the network. So what you see here, the static MD, for example, scales very well. It does not move at all, so we have a constant delay bound and constant lifetime for different network sizes. And here's one example for which it does not scale so well. So the random walk keeps the lifetime approximately the same, but the delay bound goes up if you increase the network. So the good part of this graph here is, of course, the upper left part, and we see that MD is staying in there. It goes down a bit. This is due to our strict lifetime definition, but it can keep the lifetime up. Okay. So to conclude, we have proposed a flexible heuristic framework to design trajectories for multiple mobile sinks. And we've seen especially our MD strategy can keep a high lifetime and a low delay for an increasing number of nodes. So there are certain generalizations possible or can be thought of. We could use linear transformation to go to ellipsoid shapes, so if you make the linear transformation to a circle with ellipsoids. You could use different speeds to serve clusters of nodes and move fast through sparse areas. Or you could do something by it and change the underlying distance norm completely, so you get squares and rhombuses instead of circles. Okay, these are the references from the papers we choose more competitors from, and thank you for your attention.
Some questions? So I was curious, actually, in some of the slides you showed with the performance, there was one in particular where it was number of backups versus total energy consumption. And it seemed like total energy consumption only got up to about 15%.
Yes.
That's because you're defining the end of the lifetime when the first node dies.
Yes.
So have you looked at the distribution of energy remaining at the other nodes when this network dies? And in many cases, if one node goes down, the network can still persist. Have you thought about how that?
So we did also experiments with more nodes dying until we say the network is dead, but I don't have numbers in my head how the electric energy for the however, what we have seen in the relax with split cycle definition, we see that here we have seen that MD goes down a bit. Okay? It goes down from 11 to 8 between these network size. If we relax this lifetime definition, we see that MD can stay here at 11, but the other approaches, they still drop down for increasing network size. So this is
Did you report on that in the paper?
yes.
Any other questions for this weekend? Oh, if not, let's thank you one more time. All right, so the next paper in the session is entitled Efficient Mobile Data Collection with Mobile Collect. It's a paper by Navid, Hassan Zadeh, Olaf Landsiedel, Frederik Kermans, Olaf Rensfeldt, and Timo Voigt. Unfortunately, the first author, Navid, wasn't able to get a visa in time to make it to the conference. So the paper is going to be presented by one of his colleagues, Antonio Oliveira Gonga. So thank you, Antonio, for doing the presentation. Take it away.
Thanks a lot. So, is the disclaimer? Yes. And at the end, we can answer some questions. So, this paper talks about data collection and sports events. So, this is an example. For example, here you have a marathon and you have athletes. And the goal here is to know the position of athletes, or you want to collect vital statistics or vital signs like blood pressure or whatever you want if you are considering body sense of network, step frequency or acceleration. And you can also imagine, for example, like here, in the store of difference. And the goal here is that you want a low-cost solution that this implement does not need to recreate a new entire protocol. And here some nodes have 3G connection, or can be GPRS or 3G connected. And most of the nodes are not 3G. And they also assume that there are multiple sinks. In this case, instead of having one sink, because we will have many hops to send data to be processed in real time or whatever. But if many sinks, it allows easy collection of data, because in this case, you have smaller relay. So in this case, of course, to route data to the sinks, you need a routing protocol. In this case, each node maintains a route to the sink. So in this case, you can think that there is a protocol that collects data, for example, CTP, running on this system. And of course, since we are talking about mobility and the sinks and mobile nodes are mobile in this case, we're going to have a very dynamic network. And in this case, we're going to have routing problems. And the most challenging of them is routing loops. So the approach they have presented here is that we have already many routing protocols in wireless sensor networks. And there are already many MAC protocols. So instead of creating a new protocol or routing protocol from scratch, no, but you take one of the well-known protocols, for example, CTP collection tree protocol, the census paper, and also there is something collect. And then extend these protocols to support mobility in wireless sensor networks. So this is the main goal of this paper. So the outline for today, I will start by giving the approach, and I'll talk about the non-clustering, extending static routing to achieve mobility in this case, evaluation. At the end, I will conclude. So again, the picture here, and the goal here is to group a group of nodes in these modules that we call clusters. And the goal here is that if you create a cluster of nodes, it's always easier to route data to the sinks, because even if you have, for example, a MAC protocol that runs based on sync on clusters, it's always easier if you want to do handover from one sync to another than having a very distributed network. And the interesting characteristic here is that some nodes here can stay together during seconds or even minutes, because if you are running, you expect to be with your colleague running mates for some time, but if you want to overtake them because it's a competition, then you advance. So in this solution, the red nodes, for example, are sync nodes that collects the data because they run together with the other athletes. So, and the black nodes are the normal nodes. And in this case, the red nodes that are the sync use GPRS and the 3G node because you want to see the data as fast as possible. So the solution is based on static routing protocols because they are already very well tested, they are efficient, and we have numbers for them. And in this case, they choose well-known protocols like Contiki Collect. So for people who don't know, Contiki is another operating system similar to DCOSS'12, most well-known, but there is another Contiki. And also another protocol, they use existing MAC protocols. AMAC is also a well-known MAC protocol. And then they add fixes to these protocols in order to achieve mobility. And they do 3 fixes. Basically, the first fix is packet loss, the second is loop avoidance, and the third one is neighbor discovery. So in the first fix, what they do basically, so you have here in traditional MAC protocols, or if you transmit a packet and the packet fails, basically in your MAC, when you program your MAC protocol, you set retransmissions, how many retransmissions you want to have. Or when you transmit a packet, you can set how many retransmissions and the packet will be retransmitted. Instead here, they don't do it. What they do basically, if I fail to transmit one of my parents, assume that my parent is gone because I was depending on my neighbor that is here. But if I cannot send a packet to him anymore, I will assume that he's gone already. Then I'll try to the next one with my routing table. So in this case, instead of sending to the previous, now I select the next one. So that is the fix they do in packet loss. The second one is loop avoidance. Whenever you have a routing, one of the big problems is always having loop avoidance. And normally, if you have frequent parameter changes, the probability of having a loop is very, very high. So in this case, what they do is that, and when a node broadcasts the beacon, it also includes the ID of its parent. In this case, if I want to send a packet to a node, and I know that each parent is equal to mine, I have a probability of having a loop is very high. So instead, they don't do it. They find another way in order to route data. So the third fix they do is neighbor discovery. So since we have a very dynamic network, both the sinks and nodes are very mobile. So the probability of having your routing table increase, because in this case, you store nodes, but somehow many of them they are already out of your range. Then you still have your increasing your routing table, so that's not good. And then what they do basically, they integrate the routing beacons to map beacons. So in reality, what you do, you take routing information, you piggyback it in the beacon information, which means whenever there is a packet transmission, or whenever the MAC sends a beacon, the routing information is already in the beacon, so you can extract it. Since the MAC protocol sends these beacons quite often, then you can update your routing metrics quite easily. So this approach is used in receiver-initiated MAC, like AMAC. So evaluation. So we evaluated their approach in 3 different ways. One is simulation-based. The second, they use a robot, test it, and the third one, they use the real test bed. So for simulation, what we have here is that we have in the x-axis we have node density, and in the y-axis we have reliability. And they compare it with config collect, what is the standard protocol that exists. And then they increase the speed from 2 to 8 meters per second, and also from 5 to 15 meters per second. And what you see that their solution actually, the top line, their solution achieves a better reliability. So what you can see here, that gray area, is that if you have a density until 5, basically the reliability increases very good. And then it stabilizes around 5, almost around 10, and then you can achieve 100% reliability. So this was a setup with 50 nodes and 3 sinks. So energy in this case is not evaluated here, but since the approach uses AMAC have all the values and numbers in terms of energy consumption. The second one is a random point. In this case, what the evaluate is, so in that graph here, that most graph here, the density of nodes in the x-axis and the y-axis for the energy consumption. And what you can see that if you increase the density of nodes, so the energy decreases. So that's simple, because if you increase the number of receivers in a field that can handle your data quickly, so it means that you will not fail that much. So you have always someone close to you to hand over your data. And the second one is interesting, is that reliability is a function of density. So you see here from 0 to 5, the reliability increased quite a lot, but then it starts to decrease. So this can be explained by the fact that if you increase the number of nodes in a field, basically you are increasing interference, because most of these MAC protocols, they don't handle completely the hidden terminal problem, for example. So in this case, you will have a bound where you cannot improve more, and then you start, your reliability starts to decrease. So basically, you can see that there, but then there is a slightly small improvement here. So the conclusion is that they introduce mobile collect. So it uses tree routing to collect the data in mobile settings. They got very good, very good results, and instead of building everything from scratch, now they use existing MAC protocols and existing data collection protocols. They apply prefixes to those protocols, and then they have the solution for mobile data collection. Thanks a lot.
It's very brave. You said you would take questions, even though these are not on paper.
So if you have some
give us
questions.
some questions. So are there any questions for the speaker?
as you introduced previously, you said whenever the packet loss occurs, you will try to rediscover the current of the load and without employing the traditional retransmissions. But my question is that with this solution, because in the sensor network, the transmission would be heavily affected by the quality of the channel. Especially you say your application want to be used on the sport sensor nodes, which will attach on the human body. So I mean, in this case, if you use this, you call it an improvement, but I don't think it will be cost efficient if you just reselect the parent if the packet was caused by the poor quality of the channel.
That's true. I agree with that. But so that's one assumption they do in this solution. So if you lose a packet, you try to transmit. If you lose a packet, then since everyone is moving, you assume that he is not there anymore. Because if you think in a fixed topology, if you fail once, then if you wait some milliseconds after, you can retransmit again, because in this case, maybe the channel conditions are better now. But in this case, you don't know if you're running, then you don't know if you're out of range already. Then maybe it's not feasible to retransmit to the same guy. Then try to select the next one that is close nearby, and probably your packet will go through. I think.
I'll repeat the question. The question was, had the authors tested their solution in a real implementation where the sensors are worn by human athletes?
No, because they test in simulation, and then there are 3 evaluations they do. Simulation, robot tested, in this case to test the handover, and then they have something in the test bed. But I don't think that they had real sensors attached to the kits.
So, thank you very much, Antonio. Great, so final presentation for this session will be on the paper Throughput Maximization in Mobile Wireless Sensor Network Scheduling with Power Control and Rate Selection, and it will be presented by Joseph Alejo.
Thank you very much. So my talk will go through introduction, model, algorithms, and concepts of simulations. So the problem is we have access points, machines which are scattered around in the region, and they can employ K transmission rates with K transmission powers. And you have mobile users that are roaming in the region, and each user is associated with a job that has a weight, and the goal is to assign the time slots on each access point to the jobs with adaptive transmission rates and power control, so as to maximize the total traffic of all assigned jobs. And you want to prevent the interference among the access points, so that no 2 access points transmit at the same time. So the assumptions in the model is that each job is associated with a single data item that needs to be transmitted, and the scheduled transmission starts at discrete time slots. And the data items are transmitted in continuous time slots, so we don't allow any preemption, and each channel is dedicated only to a single transmission. So you have a mutual exclusion. So here's the scenario. You have here 5 access points, and you have 2 users roaming in the region. we need to assign the time slots on some of those access points to those users so to transmit data to those users. So since you can employ different transmission rates and employ different transmission powers, you have each of those will give you a different transmission range. So with the transmission range, you can control when the user comes into contact with the access point. So the higher the transmission range, the bigger the contact window that each users have with a given access point. So using the Shannon's formula, you have the capacity channel, which is related to the power, transmission power, and the range. And the rate of transmission is bounded by the channel capacity. So if you can control one or the other parameter, you can control the rate or the power, or both. So if we keep the power constant, if we increase the rate, then since the rate is bounded by the capacity, the transmission range is going to go down, so the contact window for each job on that particular machine will decrease. At the same time, if the data size S, the transmission time for the particular data size is also affected by the transmission range. Inversely, so if we increase the rate, the transmission time for the particular data is also gets decreased. So the increasing the rate has a twofold impact. Increasing the rate will both decrease the contact window and decrease the transmission time, whereas the decreasing the rate will both increase the contact window and increase the transmission time. So here's the picture of the Shannon capacity. So when we employ the rate 1, we have a bigger contact window. And we employ the rate 2, which is higher, we have a smaller contact window. But at the same time, we can transmit the data item with this duration of time for the rate 1 and with this duration of time for the rate 2. On the other hand, controlling the power, if we can increase the power or decrease the power. So increasing the power gives a higher transmission range, so it will increase the contact window. But the problem is that it will create the interference. So we want to balance all of those parameters, and we can formulate the problem. So we have M access points, and we will index them by KL. We have N jobs, we'll index them by IJ. And each of the machines can employ a discrete number of transmission rates and discrete number of transmission powers. So the release time and the deadline time is going to depend on the job, on the machine, on the rate, and on the power. So the contact window is going to be this. And the processing time will depend also on the job, on the machine, on the rate, and on the power. So the processing time is this. And each job is going to be associated with some weight. And we can also associate an interference matrix for a pair of two machines, employing the given powers and given rates as a 0-1 matrix if two machines employing the rate and power do not interfere and one otherwise. And we associate the indices as usual time slots, and they associate the binary variable x, j, k, rho, pi, s to be 1 if the job is scheduled at time slot s, on machine k with rate rho with power p, otherwise it's 0. You can formulate this as a IP program where we want to maximize the throughput of each scheduled job for each job on each machine with each rate power, with each rate, with each power for different contact windows, subject to those constraints. So this is the first constraint is prevents that no jobs are scheduled at the same time simultaneously on a single machine. The second constraint prevents that any single job from being scheduled more than once. And the third constraint prevents the interference, and it wasn't just the binary constraint. Now, we study just the rate selection problem. Well, we can, and using the powers, we can eliminate this summation, and we can eliminate all the rows in the constraint. Or if we just study the rate selection power, we can eliminate the power selection from the formulation and from the constraint as well. So the problem in literature is known as the throughput maximization, and the first two papers we studied the unrelated scheduled machine problem, and for the job-dependent windows only. And the first paper they give a approximate solution for the unrelated machine problem, and for the second paper they improve the approximation ratio. For the fourth paper, they consider the problem where the jobs are also machine dependent. And the third paper, they consider the jobs both job and machine dependent, but they don't consider the rates and powers. So in our problem, we extend the problem when we consider the rates and powers. So here's a simple example. Let's consider there's a rate selection. We have two machines, two jobs, deploying two rates, and basically, so we have two jobs on each of the machines. So the simple solution for that problem would be we can schedule the J1 on machine 1 with the rate 1, and then J2 on machine 2 with the rate R1. But is there a better solution that deploys only one machine? Well, there is. We can schedule both of them on machine 2, the job 1 on machine 2, then the job 2 on machine 2, and they don't overlap. So the problem remains NP hard. So what we do, we are